Right.
Okay, well, we'll go ahead and get started. I want to welcome everybody. I believe everybody on the list has attended before. Whoops. Is that correct? I'm kind of multitasking here, but I believe everybody has been to one of our sessions before.
Laura Bean is a new person that joined us today.
Oh, okay.
So we have one brand new person. Laura,
Okay,
do you want to unmute and introduce yourself?
Yes, good morning, everyone. My name is Laura Benjamin. I'm a graduate at Nova Southeastern University with Master's of Biomedical Informatics. And Professor Patricia Kopp invited me, so thank you for the invite.
Sure.
Okay, well, it's great to have you. What I'm going to do is I'm going to start with the homework assignment quickly, and then I'll also post the homework for today. So let me find it first here. This was a simple two-part exercise where we just wanted to show the nomogram, which is kind of an old school idea when you open it up. I remember these from years ago where you looked at the risk factors and you shifted it like, for instance, major vessels colored really means how many coronary arteries were calcified on fluoroscopy. And the idea here is, well, what if you say, well, they had 1.5 to 2.5. What did it do with the probability that they had heart disease? The answer is it went from a baseline probability of 45 to 80%. So it simply gets you to understand that you can, with a nomogram, play with the risk factors to see what's most important. This really preceded machine learning to a large degree. We did this with odds ratios and logistic regression years ago. So you can move this, for instance, let's do ST depression all the way down here. If they have no ST depression, the risk goes from 45 to about 28% roughly. So this was just an exercise to get you used to using a nomogram. It's kind of an old-fashioned way of looking at what risk factors or predictors are truly important. The second one was just getting you an understand JASP, which is a great statistical package, starting off with some simple stuff, such as I took the numerical variables and drug them over here. So you've got age, resting, systolic blood pressure, cholesterol, maximum heart rate. And then I did correlation plots. And again, you just hit this and now you've got a full screen. So you get this descriptive statistics in this table. You can look at the distribution, and I would say this is only slightly shifted to the right. And because this has a couple of outliers up high, perhaps this is slightly shifted. But the main thing is when we do exploratory data analysis, we're very interested in relationships and correlations. So doing this for all your variables, all your numeric variables makes sense. So what, for instance, in this case, age is here, resting systolic blood pressure goes up with age. We know that the blood vessels get stiffer. So instead of being 120 over 80, maybe you're 140 over 80. Cholesterol goes up with age. Maximum heart rate. Now, this is the maximum heart rate on a treadmill. Maximum heart rate goes down with age. You just don't tolerate exercise as well. So that the ability to get a high heart rate on a treadmill is less. That's all that I want to glean out of this. Others, for instance, there's no relationship there. But I wanted you to get used to using tools like this when you have a new data set and you're exploring it and trying to figure it out. I think it's very useful. Okay. And again, I'll try to remember to put the new homework assignment there in a minute. Now, I mentioned in the email that I was going to show you a new large language model called GraphGPT. Well, I'm going to show you two, as it turns out, for totally different reasons. So GraphGPT looks like this. You put your prompt in of what you want to display, but you do have to have an OpenAI API key, which you just go to OpenAI, you have to register, put a credit card. The cost is very, very minimal, just to, you know, so you don't worry. And the end result is you put text in. A 44-year-old woman with a history of obesity, diabetes, hypertension presents with 3 days of sharp right-sided chest pain made word by coughing. She's had a history of tuberculosis, 20-year pact of smoking, and it generates a graph like this, if you can see that okay. So that's an example of a medical one that I just put together. I'm sure you could design one better. How about a non-medical one? What about trying to do an association of the Starbucks in New York City, where you tell it, you know, the Bronx has 40, Staten Island has 3. And so here's the non-medical, what it looks like. And you might say, well, so what? What's the big deal? The big deal is we are moving towards combining large language models with graph databases. One of the most popular graph databases called Neo4j, they now have an AI component. So as I put in the summary here, it is hoped that AI can not only create complex graph databases, but it can query them as well. So my vision for this is you will do a prompt or upload text and it'll create the database, followed by a prompt asking how you want to query it. Because otherwise, the two leading graph databases require separate languages to query. In other words, it's not SQL. It's one of them cyber. So my point is, I hope there's a bright future, because otherwise graph databases are a bit difficult. So the comment by David, yes, but the cost is, it's like pennies for 100 words. So don't worry about the cost of that, but I'm not recommending this really at this time. What I'm saying is stay tuned, because this will be very powerful. Remember that you can analyze, let me just see, you can not only analyze the node of woman here, you can analyze the edges, which in this case would be habit. It's more robust than a relational database is. And so in medicine, we hope, and in fact, Google and a lot of other businesses, you probably don't know this, Amazon uses a graph database. They don't use a relational database. In medicine, we're just now seeing that. So this is just a way of giving you an intro to graph databases. All right, the second one that I think is interesting that, yes, I only uncovered this week is called Claude AI. Now, Claude was designed by the same people who left OpenAI and started their own company. It's beta, so you don't pay anything, it's free. I think the largest difference, the greatest difference between this and ChatGPT is that, notice I have a CSV file here of heart disease, the same heart disease that we've used a million times in Orange, but a PDF or a CSV can be 75,000 words. ChatGPT has a limit of about 3,000. What does that mean? It means that you could upload a monograph or a book of, say, I'm guessing 300 pages, and it will summarize it and digest it. So let's look at this for 1 second. So this is Claude. I uploaded a CSV file and I said, summarize this data set, analyze the data set using logistic regression with outcome being diameter narrowing, that's the outcome, report recall precision and F1 score. It did actually a fairly amazing job, but you gotta look at it in detail. I've seen this mistake before. The abbreviation THAL, they said, stood for thalassemia. Wrong, it stands for thallium stress test. And then, so it tells you what's in the 0 class versus 1 class. It was correct on that. It did fit the model or train the model correctly. That divided it into train and test. Great. So it's just like Orange up until the results. The results are far lower than Orange. Don't ask me why. Remember, this part of it's a black box. In Orange, you can pretty well see every step. So, you know, what would I say about this? I would say this is a beta tool. It's very interesting. Stay tuned. Maybe a year from now, it'll be even better. But I don't think I can trust it yet. It's on the right path. It will do the code for you. For instance, here, I asked it to do a histogram. It will not display anything, but it will create the Python code, and you could copy this and paste that into a notebook, like a Jupyter notebook, and you would get a histogram. So I will play with it further. You all should feel free to play with it also as a competitor to ChatGPT, but I don't trust it, unfortunately.
Bob, I have a question.
Sure.
Did you ask like this Claude to give you back like the code that he used to make these results or no?
Yes. And again, you can get the code, you can say display the code.
Okay.
But what's really strange is both use Python. They both, I made sure that my train test split was 80-20.
Okay.
Yet I got results on the test set, not the training set. Quite a bit of difference. This is probably in 0.8. This is like 0.85. This is like 0.85. So very different. I don't know why. But that's only one data run. You know, I'll do more testing. But again, a word of caution. The other thing is that I need to emphasize, and I'm sure you all have seen this past week, there's a $3 billion, that's with a B, billion-dollar lawsuit against Microsoft and OpenAI for a violation of privacy. I don't know where that's going. This week, the FTC said it's looking at ChatGPT for possible harm or problems with outcomes related to the user. So I kind of predicted this 6 months ago, or, you know, around when ChatGPT. Just understand, you're only now seeing the legal implications. You haven't seen the financial implications yet, really. You haven't seen the unintended consequences yet. You haven't seen the security hacker, you know, things yet. So all these players are happening at the same time. And so there's no question that these large language models are kind of earth-shaking developments, but where they'll be a year from now or even 6 months from now, I really don't know. But I think most authorities are saying it's too soon to think of them as anything but an experimental, highly interesting platform. And I'm going to leave it at that unless there are questions. Are there questions about that? I know how controversial this is.
Just a comment. I think they're coming out with Claude 2 pretty soon.
What's that?
Claude 2, they're coming out.
This is Claude 2.
Oh, this is Claude 2. Okay, all right.
Yeah.
Okay.
And again, there'll be rumors of ChatGPT or GPT 4.5 and 5. You know, that's just the way it is. So they're all evolving, whether they get better. And as I think I mentioned last time, there are 10 biological or biomedical large language models, none of which have been released. Most are being beta tested. We don't know if they're going to be better than just a plain old large language model. It's not a given that they will be better. They might be. So anyway, we'll continue to discuss that. Feel free to email me, but I'm going to go ahead and go back to chapter 4. I think we may have done a little bit of skipping unintentionally last time. I think there was an audio glitch or whatever. Let me try to center this. Can you all see this section, how do models work?
Yes.
Okay. The big picture, which I think is really the important thing, is what is a model? In this case, this is again, supervised learning. You know the outcome. You're trying to predict outcome with data, particularly then and tested on data it has not seen. So basically, what computers like to look at is one and zeros. That's what they understand. So these really are vectors that are matrix in a vector. So the predictors are one and zeros, like could be smoking, cholesterol, whatever. The outcome is 1 and 0. One could be has heart disease, 0, no heart disease. And these are inputted into a machine learning with multiple algorithms that learn patterns, basically, learns relationships, and creates a model that you can tweak the algorithms and create multiple models and pick the one that's best, but then you feed it data it's not seeing. And we'll talk about validating the model when we talk in chapter 5. But it's important to understand that computers need 1 and 0s. In fact, when we get to images and words, natural language processing, that's all converted into vectors and matrices, 1s and 0s. Pixels are going to be numbers, and that way you can have computation. So it doesn't interpret words or images. It has to be converted to something numerical. All right, so another way of looking at this, well, let me just read this. Machine learning involves using data to create a model that learns from the data by identifying patterns and relationships between input predictors and an output target to make predictions about future data. That's, I think, an important thing to understand. And also, we may use the terms like the model fits something. Fitting and training are the same thing, just so you know. And let me skip down to this where it says we're comparing a statistical model with the supervised learning model here. All you need to understand is this equation, y equal g times x1 through whatever x number plus e for error. So y is the outcome, let's say heart disease, g is the algorithm, whatever algorithm you select, and then x1 to xn are the number of predictors plus some type of error function. So error, we're going to immediately go to this idea of error and show you residuals. And I think in a way, picture's worth 1,000 words here. So this is a residual plot. It's most commonly comes up with linear regression. But let's apply some common sense to what they're doing. So this is predicted data on the y-axis, and this is actual data. So if it predicted something being 30%, I don't care what it is, and it is 30%, so predicted is 30%, the actual is 30%, it'll fall on this 45-degree line. Does that make sense? However, nothing's perfect in life, so you see what amounts to be sort of outliers here and here. This is pretty good in terms it's pretty close. Whatever is predicted over here is pretty close to the observed, but these errors are also called residuals. So one other concept here that's easy to understand, I think, is so this might be plus whatever it is, plus 10, and this might be minus 8, let's say. And so when we talk about linear regression, we'll be talking about root mean square error. Why is it root? Well, the square root of minus 8 becomes, or not the square root, but the square becomes a positive number. So square of minus 8 is 64, whether it's positive or negative. But the point is, the error is how far a predictor is from observed. So this is a scatter plot. You don't have it in the text I sent out, but I did send out how you can create that if you like, if you want to see it. And the second plot does basically the same thing. This is a histogram instead of a scatter plot. So here's 0, where you would have 0 errors. Here is where the actual observed is higher than predicted. And over here, where it's lower than predicted. So no surprise, it's kind of a bell-shaped curve. because again, you're going to have, just like you're going to have false positives, false negatives, you're going to have a distribution of errors. So again, you can read the fine print, but I think it's just important to understand the 40,000-foot view of what supervised learning is. The other thing is we throw out the term labels. That is same thing as target, outcome, class, or Y variable or dependent variable. They all mean what it is you're trying to predict. That's the outcome. So that make sure you understand that. So Dave, I'm going to turn this one back over to you. Are you going to need the screen, or are you going to go just verbally go
If you
over?
scroll down a little bit, Bob, then I'll just talk to, if you go down to the overfitting, underfitting, we covered this last week. And that's all Bob and I agreed on is on this section. If you stop right there, Bob, that'd be great. To just talk about, just to remind everybody that these machine learning models, they're really trying to find a good balance. You know, you could be overfit or you could be underfit. And the machine learning, by trying to find, always try to minimize the error, is going to try to always find the good balance. You don't always get that when you're in the world of statistics, because you might get an automatically more of an overfit model. But in the machine learning world, you get this automated balance. And how does that happen? Well, it forces you to hold some of your data back, and then you have to predict it. And just by trying to predict some of the holdback data you get, you're going to very often protect yourself against overfitting, just by the nature of how that model was set up and by using the unseen amount of data. So that's why I want to mention there is just a brief reminder of last week, because it's such an important topic. So Bob, I'll hand it back to you.
Okay, thanks. So you will see when you read any kind of data science monograph about model interpretability and explainability, and I want to say up front that I think these are terrible terms. Everybody has a different definition. It's very confusing when you read it. I think they should abandon that and just say model transparency. I mean, I'll give you another, I'm just going to read it, that a more accepted one for interpretability is cause and effect can be determined. However, even that I don't like, because so often you're showing causation, or excuse me, showing correlation.
A bag of ice, morning.
Showing
A bag of ice.
Could you mute?
Ice
Please.
cubes.
Yeah.
Sorry, one. Yeah.
So often you're showing correlation and not cause and effect. And one of the definitions for explainability, it can be,
Right there. Yeah.
okay, if you're not presenting, can you please mute?
492.
Okay, so under explainability can be explained by human language or terms. But again, I think these are bad terms. I think basically we're interested in, is the model transparent? And that would be called a glass box, or is it a black box? So we'll be looking at different methods to try to open the black box, if you will. The classic statistical methods, such as logistic regression, linear regression, decision trees, and I would say naive Bayes, are glass boxes because they have things like coefficients that you can measure and interpret. But things like boosted trees, XGBoost, or neural networks are black boxes. We'll be going over some of the ways to get around that I won't really spend too much time on right this minute. Lime is one that was an early one that's not available in Orange or JASP, but has been used. The one that's more common and more current is SHAP, which is a way, what will happen is if you use this, you can then say, well, XGBoost saw coronary calcifications is the most important, thallium stress test is the second, and we'll go over that when we get to chapter 5 on how you evaluate a model. And then we'll also go over something called permutation feature importance, which is the most common sense of all. All it means is what you're going to do is, let's say you take a predictor like the number of coronary arteries that are calcified, and suddenly you shuffle it, you just scramble it and see what happens to your AUC. If your AUC doesn't change at all, it must not be an important predictor. Does that make sense? To me, it's the most common sense method there is. So on the other hand, if you shuffle the data and the model suffers a great deal, then it must be an important predictor. So that's all permutation feature importance, or PFI. And don't worry about it. We'll be going over that later. I'm going to turn this back over to Dave, and you want me to stop share, Dave, and you want to grab it?
Yeah.
Rob, I have another question.
Okay.
Like this thing of the permutation, like of the shuffling, like do you do one column at the time, or is there like, are there strategies to do like multiple column? Because I feel like if you have many features, you have to repeat it like too many times, right?
Well, it would involve all features. You're talking about like SHAP, SHAP?
No, I was thinking about the last one you said. So you do it to all
Oh,
the features?
yeah, you do it one at a time.
Okay, okay.
But it's Orange offers that, by the way, and it is an easy one. Keep in mind, it doesn't always agree with the others. It's the funny thing about data science. So we'll be going over that in chapter 5. Dave, go ahead.
Thank you.
Okay. Can you see my screen, what I'm sharing right now? Gradient
Yes.
descent?
Yes, we can.
Okay, great. So gradient descent is an interesting algorithm. And what it's looking for is trying to find the lowest error rate in the model. And, you know, as a model's going through and trying to calculate and predict something, it's going to come up with something. It's going to say, it's going to self-check itself and say, all right, this is how much error we have. And what gradient descent does, it tries to bounce around through the model and try to find the lowest point in the valley, so to say, whereby in this valley here, the y-axis is the loss or the error in the model. Now, sometimes when these gradient descent algorithms are working, it can get a little bit tricky. You could find, for example, you go down the hill and you find a valley, and you could say, oh, okay, this is the lowest error I could get up, because going to the right, it's my error is getting higher. But if you kept the model going with more iterations, you would find that there is what is referred to as a global minima. And you would find that there's actually a lower place in that model where it could have a lower error. So how do you, when you're running a model, how do you know where you are? The only way that you could test this is by trying to really run it longer, give it more epochs, give it more time to run, more iterations, and then with the hope that you're going to find the lowest point in that model that has the lowest error, and we call that point the, you know, the optimum or the global minimum. So that's the story on that algorithm. Now, Bob, you're going to go back and do your algorithms, and I'll pick up again at 4.4.
Yeah, let me find, can you stop share? Okay.
Yep, just stop sharing. You can pick it up from there.
Okay. So when we talk about algorithms, can you see my screen okay?
Yes.
First of all, I want to emphasize that we have created quite a few different, let me scroll down here, appendices. So there's data science experiment, how to do experimentation. Here are cheat sheets for data science, data visualizations, appendix, machine learning algorithms Dave just put together. Do you want to comment on Appendix D, Dave?
Yeah, there's a lot of different algorithms. If you look in orange, you could get the impression, well, it's maybe only got 8 or 9 different algorithms. But if you look at the different default settings, like if you go into, let's say, linear regression, well, linear regression is one widget. But within there, I could get Ridge, I could get Lasso, and I could maybe even get Elastic Net. So there's a lot of more algorithms than meets the eye. So that section in the appendix tries to spell them all out, highlight them, show when you could use them if it's just on tabular data or elsewhere. So it's another kind of cheat sheet for you.
Great. And then so there's data resources for you that I probably need to constantly update. Every week I find new ones. It's almost an impossible task. Dave put together a very interesting glossary that we'll share at some point here of using formal definitions and informal definitions and analogies to get you to understand terms. Any other comment, Dave, on that glossary?
Yeah, we're experimenting with what helps people learn a lot. I have over 160 books on advanced statistics and machine learning. And a lot of times it's like you got to know the secret handshake or the knock on the door to get in. They have this special vocabulary, and it's kind of like it's a speed bump. It's almost like a special club, and they don't want you into that club. And it's always annoyed me that why haven't people taken the time to really try to explain these in very common terms? And what I did on this shot on the glossary, I took, I think it's about over 110 of the most common phrases and terms that we use in the headers in our books and tried to explain them purely with analogies, so that if somebody doesn't have any background in the true data science vocabulary, that they're going to have a good shot of understanding that. So that's one of our contributions we're trying to do to make things easier for people to not only do data science, but understand it.
Okay, thanks. And the last one is a video catalog. So we've got mainly StatQuest and other well-recognized videos, but Dave and I are talking about adding some videos of our own for key topics, such as the confusion matrix, just a variety of things where maybe a video specifically on Orange for a specific topic for 3 minutes might make the difference between you understanding a concept and not understanding the concept. So I think it's very likely before this book is ever published that we'll do that. So just be aware there will be a variety of other information. Okay, I'm going to go back now, and we're going to be talking about some of the algorithms in Orange. But let me say, the time I go through this, just try to understand the general concepts. I think you'll need to go over algorithms 2 or 3 times or more to really embrace the fine details. So right now, for instance, the 7 that I'm going to review, all of them do classification and regression as just one example. But I want you to have the big picture right now, and with repetition, you'll have the little picture. Orange has the advantage of having a lot more algorithms than most of the other data science programs, and you can run a bunch of them at the same time, and you can toggle between training and test results. That's also unusual and is a wonderful teaching advantage that other programs don't have. So just to make sure people know, you can right-click any widget and go to the help menu. If for some reason that fails, you go to Orange Data Mining, their website, scroll down to the bottom where it says widgets, and that'll give you a full window of the help menu. So we are going to talk a little bit about the fact that you can tweak algorithms, but we're not going to go into a whole lot of that. And let me say that there's a difference between model parameters and model hyperparameters. Model parameters are what the model learns on its own. For instance, if you had linear regression, it decides what the coefficients are, you don't. Whereas model hyperparameters are something you can adjust. And we'll mention that in just a minute, but things like the depth of the trees, you can set that. So there are some simple hyperparameter things we'll show you, but that's a little bit beyond the scope of what we're attempting to do. So just bear in mind, you probably are going to accept the default. All right, well, let's start with the constant widget where you say, what? What's a constant widget? Think of that as your baseline prediction of accuracy. You've got a bucket with 95% green marbles and 5% red marbles. If you stick your hand in there and grab a marble blindly, there's a 95% chance you're going to green one, right? Well, all this constant algorithm does is when you look at the accuracy, it's going to tell you it's 95% accurate because it's going to do whatever the majority class suggests in that regard. Therefore, if you want a higher accuracy, your algorithm has to exceed 95% in that case, but it gives you a baseline. That's all it does. All right, K-nearest neighbor has been around for a long time, and again, can be used for classification regression. It's all about distance, and you can use Euclidean distance or a variety of other ways, but it basically is all based on distance. And I'll go straight to the diagram here, where let's say you have a new data point that you're trying, and the question mark here is the data point, and you don't know whether it belongs to class A or class B. And that could, again, class A could be heart disease, class B is no heart disease. So you can set the K as 3, 7, 5, whatever. If you set the nearest neighbor to 3, it's going to probably say it belongs to class B. You set it to 7, and it's going to probably say it belongs to class A. So one of the drawbacks of K nearest neighbor is you have to play around with the K, and you can adjust that. So because you can adjust it, it's a hyperparameter, and see what works best, okay? I think my advice to you is we don't use it much anymore. It's outperformed by most other newer algorithms, like, for instance, random forest. It is one interesting thing, though, when we start talking about how do you handle imbalanced data? You know, the class you're interested in, for instance, let's say cancer is only 5%, 95% is not cancer, it's a benign biopsy. How can you improve upon that? And one of the tricks is software called Synthetic Minority Oversampling Technique, or SMOTE. It uses K-nearest neighbor to find minority samples that look similar, and so it helps you suddenly generate more minority examples. So that's how K-nearest neighbor is used most these days as part of SMOTE. Don't worry about SMOTE. When we talk about model challenges, we'll be going over SMOTE. All right, decision tree. I think most of you understand that. It's a great way to do a simple exploration of data. But again, it's been replaced by newer types of trees that we'll talk about. But its claim to fame, as you can, and I don't know, I guess we had the image of a tree in chapter 2 and chapter 3, but basically it based on math, it decides what's the most important thing to split on first, and then it can keeps on splitting. And therein lies the problem. If a decision tree keeps splitting, it's going to look at both signal, the good stuff, and noise, the bad stuff. So in essence, it's going to memorize good stuff and bad stuff. But you can prune it as a hyperparameter. You can go in and say, man, stop after 4 divisions, prune it at level 4, and chances are your performance will be better. So that's an example of how you can adjust it, but it's also a good example of overfitting. If your tree keeps on splitting, say 20 times, 20 levels, and so you get great results on the training data, but horrible results on the test data on data it hadn't seen before, that's proof of overfitting, okay? So that's, again, the big view that I want to leave you with. And there's a StatQuest video on it. Now we enter what are newer trees. These are called ensembles, random forest, AdaBoost, I'm showing you, and gradient boosted, all new types of decision trees called ensembles. Ensembles just means you've grouped together a bunch of algorithms for more benefit, or as this say, it combines a bunch of weak learners, trees to become a strong learner. Random forest, what we want you to understand here, and we'll have a couple of diagrams, is what it's doing is it taking bits and pieces of trees and analyzing the models and then taking a vote, if you will. This is parallel learning. It's a parallel fashion, not sequential. And then it takes a vote of what's most important and then accepts that. So, you know, we're not going to show you how to tweak it. I will comment that it does have a box in there that you can check. If you have imbalanced data, it can add weights to the minority class. Again, if you have very few cancer patients and mostly benign patients, you can add more weight and the model will improve. These newer ensemble trees, like Random Forest, XGBoost, are way more forgiving about a ton of things. More forgiving about missing data, more forgiving that if the scales are different, systolic blood pressure is 200, C-reactive protein is 2, you don't necessarily have to normalize things. It automatically takes categorical data like benign and converts it to 0 for you. So, and imputes missing data. So it does a lot of pre-processing in the background. So that's why the Random Forest and XGBoost, as an example, are way more popular. And again, you're going to need to read this several times, but this parallel analyzing of random trees is called bagging or bootstrap aggregating. I don't think you need to worry about the terms too much, but understand, and I've got two diagrams here where you're taking parts of the decision tree in tree 1, 2, and 3 and do a majority voting and come up with what your final class determination is. Now, AdaBoost comes first because it's the oldest, but we don't use it much anymore. I'm just mentioning it. You often will use it, but most people have migrated to much newer ones. Now in orange, you'll have gradient boosting, but open it up because, in other words, double click on it. And what you'll find is gradient boosting is a default Python package. CatBoost is newer for categorical data. XGBoost is new. And then there's one that will really confuse you. This is called XGBoost Random Forest. What this is the algorithm that's going to focus on is XGBoost, but it's going to apply a random forest approach. So it's going to do bagging on XGBoost. It's going to use parallel analyzing of XGBoost. I know that's confusing, but what we would say to you is what you can do is you can select gradient boost, then rename it, the algorithm, and you can right click any of the widgets and rename it gradient boosting. Then select it again and select CatBoost and rename it. So in other words, you can run 4 of these as part of the gradient boost and see which of the 4 performs the best. Again, they're very forgiving. As I mentioned, that's why they're in many of the data competitions, because they give great results. We won't be showing you how to tweak them. We'll get into what is regularization later. Don't worry about it. But in addition to all the other bells and whistles, this will help you get better results as well. So I won't spend time on what is regularization. So again, it handles other things. We will talk about multicollinearity, which just means 2 of your predictors are highly correlated, like income and education. That affects many algorithms, but doesn't affect the boosted algorithms particularly. It's less likely to overfit. Already mentioned, you don't have to normalize usually. It's fast. So it does a lot of good things. So bagging, notice it's parallel, it does a classify each one at the same time, whereas boosting is sequential. It does classifier 1, classifier 2, then classifier 3. So understand parallel versus sequential is a take-home point. And my last one, I don't want to spend too much time on support vector machine. The whole idea of this is it has an algorithm that creates a hyperplane that separates the two classes. And that's all it is. So you get this hyperplane in between, say, the cancer group and the benign group. And it, again, is an algorithm most people would include. It does have its pluses. It will analyze, it can be used for a linear model as well as a non-linear model. But I'm going to stop with that and turn it back over to Dave.
Okay, just a second. I'm gonna share my screen, move over. All right, so here we are. Now we're going to talk about 7 other widgets. Most of them are algorithms or algorithm processing. So the first one is linear regression. Linear regression is obviously only used in regression. You can linear regression. You can't use it for logistic, but it's a very handy algorithm. It's been around since the very early 1900s. So it's been around in the world of statistics for a very long time. There are some modern versions of it, which are referred to, they have the names ridge regularization, lasso regularization. Those are kind of in the 1950s, you know, probably 50 years after the basic linear regression was developed. These are more modern forms of regression. And the beauty of those two versions is they could automatically knock out multicollinearity, or if you have high VIFs, we call them VIFS, various inflation factors. Because if you get a lot of multicollinearity, it could do a real number on your model. It could mess up your ranks. It could make things look really rosy when in reality they're not that rosy. So again, you could use those options, and I'll show you when I get through a little bit. I'll go back into the Orange workflow and show you where these options are when you're looking at this widget. So in linear regression, and it's called a linear because it is using a straight line to make all of its decisions and recommendations, no matter what the data looks like. Now, in this case, we have here, the data is kind of following a diagonal anyhow, and then the linear regression will offer what's referred to as a best fit line. So it's a line that represents the data. And it's probably a good thing to view this best fit diagonal line as kind of like a seesaw, where that you get data on this side and you got data on the other side. And if the data is really linear, then you'd have just as many points on this side of the line as you would on that side. The only problem with linear regression is if your data takes on a C or an S shape or some other kind of strange form, then the linear regression widget and model will give you a prediction, but it might not be as good as other algorithms that can take care of non-linearity, which we'll talk about a little bit later, like a neural network as an example. So the next widget I'm going to talk about is logistic regression. So what's logistic regression? So here we're trying to predict or model a yes or a no. Like Bob was saying earlier, either the patient has cancer or they don't, or they have this disease or that disease, or if your email is spam or if it's not spam. All those types of things go through a logistic regression or similar type of algorithm that could deal with classifications. And what is classification? You either have a yes or a no, or you might have multiple. You might have an A, B, and C version of that, and not just yes and no. So the whole family of classification algorithms, or in this case, the logistic regression model, can take care of that. Now, what's interesting when you're in logistic regression and not in normal regression, you're forced to make a decision whether it's a 1 or a 0. 1 yes, 0 no. But behind the scenes, what the algorithm is actually calculating is, well, if you have below a certain value of what we're going to call a threshold, we're going to call it a 0, and above a certain value, we're going to call it a 1. And that's where you get into situations where that, these classification models could produce results that are maybe not always accurate. If you imagine, if I'm just 1% over the midpoint between being a 0 or 1, it's going to be called a 1. Or if I'm 1% below that value, it's going to be called a 0 or a no. So that's kind of the holdbacks and the disadvantages of classification modeling. And which is why if you have the choice of converting your data to pure numbers, is probably a better thing as opposed to a yes no. And I'm not going to get into this because Bob covered it in the homework assignment. Here we are back at nomograms. So how do we do a nomogram? I'm going to show you in a minute or so. I'm going to pull up an orange file and show you how to tie that into the naive Bayes widget. And like Bob was showing you earlier, you could do a lot of, with your mouse, pulling things back and forth and doing what if scenarios, and then figuring out what is the risk for either a 1 event or for a 0 event. And then so naive Bayes, and so what's that all about? It's that algorithm looks more at probabilities as opposed to the frequency of an event. And what I'm going to do right now is I'm going to pull up my orange file. Bear with me. Pull it over on this screen. Somebody let me know if you could see my orange file there.
Yes.
All right. So we have on the top, what I did, I was talking about linear regression. So if I had a workflow where that I have body fat data and I want to try to predict what's the percent body fat with a lot of attributes that I'm collecting on patients, I might put in this, I call it a horse race. I'm going to put the linear regression algorithm in competition with the neural network, which I'm going to talk about in a little bit, and then send that off into the test and score widget and see which one of them are the best. But another widget in orange I'm going to talk about in a little bit is also called stacking. And what that is an ensemble model. Now, Bob talked earlier about ensemble models. There are algorithms like Random Forest that do their own ensembles inside of that family of algorithm. But this type of stacking, or what we call ensemble, what it does, it says, you know what? And you can see how it's connected here. I'm going to take the best ideas from linear regression. I'm going to take the best ideas from neural network and see if I can maybe beat out the performance of the individual linear regression or the neural network. And then if we want to see who won this horse race, because now I have a hybrid and I got the individual neural and then the linear, I click on the test and score widget. And if you click on the test and score widget, and you could always say, all right, I'm interested in this case for R-score, and I could click it again and make sure that the highest R-score is on the top. You could see that the stack model actually outperformed the two individual models. Now, that's not always the case. It's not always, it just, oh, wow, this is great. I'm going to do this all the time. Well, keep in mind that it's not an automatic that the stack model is always going to be better, but you just don't know in advance if it's going to beat out the performance of the individuals, which is always a good thing. What you want to do is a good practice when you're really, it's very, very important for you to find the best model, that you then connect these different lines and connectors into the stack model and give it a shot of seeing exactly how good it can be. Now, and I'll talk a little bit more about these things on the right as I progress through that part of the chapter. But I did talk about logistic regression so far. Now on the bottom here, I don't have regression analysis of continuous variables. I have the heart disease data set that I just happened to put in here, which is available in orange. Here I have a categorical variable. Do I have heart disease? Do I not have heart disease? And in this, I'll call it a horse race. I'm having a logistic regression, competing against neural network, competing against naive Bayes. And by the way, the nomogram, you can see it only works with naive Bayes, and you have to connect it directly to that widget for it to do that. Now, when I talked about earlier that there's different types of options in linear regression and also in logistic regression. Let me click, for example, on linear regression and pull that over here. And this is when I double click on it, it tells me the options that I have. And what I could do in linear regression, I could select a model where I have ridge regression, which is a type of regularization, and I could move this slider back and forth of how much regularization or multicollinearity combating do I want to have in it. Or I could select lasso model, or I could select elastic net. And what in the world is an elastic net? What's a hybrid between the lasso and the ridge? The lasso is very rigid. If it notices that you have multicollinearity, too many features that are causing some issues, it's going to knock them out of the equation and demote them. Now you get the same advantage if you click on logistic regression. You know, I have here, I could do ridge, or I could do lasso, or I could do none. So I have different options. And like Bob was mentioning earlier, I could copy and paste a few of these widgets and make one of them no regularization, one of them with ridge, and one of them with lasso. And then I could automatically then wait and see what the test and score widget, which one of them actually performs the best. And I could also, like I did on the above over here, I could do a stacking of an ensemble between these different algorithms. So now at the moment, I'm going to switch back to the materials before I talk more about what's going on there. Neural networks. Neural networks are very highly advertised way of an algorithm that can supposedly think like the human brain does, you know, with the way that the human brain has its neurons, and then, but it's very complicated. It could also deal with regularization, so it can combat multicollinearity. And it can be used for not only tabular data, but also for image data, and also for natural language processing. So it's a pretty versatile type of algorithm. And it uses techniques like back propagation, front propagation. It uses weights. It uses things that are referred to as activation functions, of which it offers 4 different options. And before you know it, you're into the twilight zone as far as vocabulary is concerned. And let me go back to my orange workflow here and just click on the neural network at the bottom, so you can see all these different options that you have. So you have neural network. So what's the maximum number of iterations? So this tells me how often am I going to allow it to search for the best answer with the lowest error rate. But you see here under activation, I have ReLU, which is the one that's we mentioned in the text, but there's a few other different options here. But the default is because that's the most popular, but it doesn't always mean that the most popular one is going to be the most accurate. So here you have a lot of experimentation opportunities with the activation. Also under the solver, it's automatically set to the default to Atom, but there's 2 other solvers. And usually the Atom and ReLU combined do pretty good, but there's no guarantee. So when you're trying to experiment with the neural network, there's a lot of things that you could experiment with to find out what's really going to give you the best option. And then you have also this regularization. So let me go back now to the materials where we talk about the neural network. So the neural network gets kind of complicated. We have what are referred to as inputs. This is where your data is input into an input layer. So let's call them numbers. They're split into different types of areas. Then you have two or multiple or more what are referred to are hidden layers. This is where the data is processed a little bit more. And the beauty of neural network is it has the option of being able to look at, is nonlinear situations. So it's trying to find patterns that are there, linear or nonlinear. And then it has an output layer where it's trying to tell you, okay, I think I know what's going on. So there's a lot of complexity going on here. And there's a lot of, then we have the neurons and there's weights that are involved. And it's very complicated to understand what's going on inside of a neural network. So what we do is we tell you to have a look at a few different of the resources that we have here on that. But also, when you get into something very complicated like a neural network, like I was mentioning earlier, that it's very interesting to have a look at what's actually, can you explain the concepts with analogies? And so that's the big question. So here we have a lot of these cryptic vocabulary that takes some study to understand, backward propagation, forward propagation, optimization of weights, neural activations, and et cetera, et cetera. So how do you really understand that? So I use an analogy here of, all right, let's try to explain how a neural network works by basically trying to explain it with a baking analogy. So let's say we have this master baker, and he's going to employ a bunch of people that are apprentices in his bakery factory to make a bunch of wonderful types of products for their customers. So what does this master chef have to deal with? Well, he has a lot of ingredients. So, and what else does he have to deal with? Well, actually, how a neural network works is they pick basically apprentices. They pick neurons that are just given randomly low weights. And what does that mean analogously in the world of baking? It means experience. How much experience do they have? They don't have much experience. So this master chef here has a bunch of these bakers that he puts into two different departments. In this case, hidden layer one, that's analogous to like these people are doing certain part of the dough prep, and hidden layer two is doing another part of the dough prep, or here the data analysis. And then it moves out to an output layer. And what's the output layer? Those are the fine pastries that are sold in the bakery shop, and we call those the outputs, right? And then this model iterates. And I showed you, if you remember, when I clicked on the model, it says 200 iterations. So it's actually, analogously doing 200 taste tests on this data to try to find out which one has the lowest error, which of the predictive models. And the whole time this is giving feedback to the master chef. And every time the master chef gets feedback of, okay, the error rate is pretty low, in this analogous story, this person is actually training then these novice apprentice bakers to do a better job in the matter of milliseconds, right? So we've created within a matter of seconds 200 different products that 200 different taste testers have tested on, and then they're optimizing the whole model. So if you look at this whole neural network system, you could say it's an analogously comparable to like a grumpy master pastry chef, which we call the gradient descent, who's always interested in getting the lowest error rate. And what does that mean? You're the lowest error rate. You want to have the lowest amount of complaints from your customer. He's using forward propagation. What does that mean? That means you're processing your ingredients for your pastries in a different way. And then he's having all the apprentices in the hidden layers or the department layers of this pastry shop do different things. And they're doing regularization. And what is regularization? Analogously in this story is what you're trying to do is not use a whole lot of one type of product, but you're trying to use a more diversity of a lot of them. And then you're trying to make each of the neurons make better decisions. And that's the technical term for that is called neural activation. So this is just a little bit of an analogous story to try to get your mind thinking a little bit in the direction of how do I understand some of these things on a very complicated topic. And so when you look at later our new glossary and you see a lot of analogies, it's kind of like our attempt to help people get a little bit out of their box of their thinking and not just dealing with very cryptic statistical or machine learning or data science topics, but try to give them a chance of understanding that. The stacking widget, I've already talked about and showed how it's piped in, and then we could always compare it as a stacking or ensemble widget actually doing a great job, or is it better or the same or worse as the old one? And then we have a save model widget. Now the save model widget is pretty interesting. And let's see if I have a wonderful algorithm. And I'm going to pull up my orange file here again. If I find out, for example, here that that one of these models is actually the best, which is the stacking model over here in my regression model here, I could attach a save model widget to it. And guess what that'll do? That'll save that algorithm, everything I did in the background, all the little tweaks, the hyperparameter tuning, anything I did. Let's say, for example, we put out a little competition for all of you and said, all right, tweak the model however you want and send me your best model. You could then email that to us. We could then, so we have to, first of all, you have to save that model as what's called a pickle file, and then we'd upload it and test it on another data set and then go into the predictions widget and see how good it did. We could see the R-squared value would do for that data set. And we could take, all these different save models, one from Larry, Mary, and Jerry, and we could see which one of those, if this was a competition, which of those models that each of those three data scientists created has the highest performance. So that's the beauty of these saving models. And the beauty is you don't have to let on all the secrets of what you did behind the scenes to make it a great model, but you could then hand it over to somebody and say, use this model for this situation, and then you could see what it looks like. So it did the same story here for regression, did the same thing at the bottom, where that in this example, the logistic regression model was the best. So I wanted to save that one, and I could send that into over here and use that for future predictions. So that's what you could do with the save model widget, and then you reload it back into a new data set and see how it's doing. So that pretty much brings us to our end of that section of the algorithms and the widgets we wanted to talk about. And I think right now we'll open it up for any questions or discussion anybody wants to have.
And I did comment that I did put the homework assignment in the chat.
Great.
Yeah, questions about what we went over? I realize that's a lot to absorb. Repetition is important. I strongly recommend you all reread this section and use Orange and duplicate the models that Dave showed you, because it's so important to practice this so it sticks and you understand it better.
And just by looking at this one picture on the video, it's very easy to recreate these models. You just pull out these different widgets, you connect them and make sure you have your data loaded into it, and then you could create these models that we've shown throughout the book in these videos here. All right, any closing comments or questions?
I have a question, just random. First, thank you both for the lecture. And second, I was wondering, like, if you train, like, someone give you a model that it was like done on a sklearn or something in Python, can you load it like here or not?
If you train a model, if you can save it in Python, as a pickle file, yes, you can. And guess what? Pickle happens to be a file format that's specifically designed for Python and only for use within Python. You can't bring it over to an R program.
Okay.
So I would suspect if you can save it as a pickle file, we can then see when you go into with this widget here, the load model widget, whether it would accept that pickle file, and I suspect it would. And then you could use it in the world of Orange for doing the predictions or anything else you wanted to do with that model.
Got it. Thank you.
Okay, next month we'll be going over more about machine learning. We will go over some of the challenges that you need to be aware of. This is not an automatic slam dunk. There are things that you have to consider when you create a model. We'll talk a little bit more about classification versus regression also next month. So any other by the ways or comments before we close? I will, of course, create the video and post it on our YouTube channel, as I always do, and I'll send out a notice. Hope you all do have a great weekend, free of tornadoes and all the other extreme weather.
Okay,
All right.
everybody, have a great weekend.
Okay, take care to everybody. Okay,
Thank you. Have a great weekend.
okay. Bye-bye.
Yeah.
Thank you, everyone. Dr.
Thank
Hoyt,
you.
Bye-bye.
Dr. Hoyt, may I speak to you after, or can I send you a message, please?
Absolutely.
Awesome, thank you. I will text you. Actually, I'm not included in the master files. So, or the master email list. So someone has to send me a link every
Oh,
week.
I will add you. My email is rehoyt@gmail.com.
Awesome, perfect. Thank you. I appreciate
Okay.
it.
You're very welcome.